For my project, I had the task to implement a model predictive control method called MPC for a racing car. The goal was to identify the dynamics of the car and develop an MPC-based control in order to achieve high performances. For the environment, we had access to a test track and a racing track. The mathematical model of the car is a tire force model, which means that we have included tire forces in order to include drift, and we have identified longitudinal dynamics and lateral dynamics of the tires. The state and input of the cars are the positions, the angle of the cars, the speed in the body frame, so in the reference of the cars, and also omega, which is the angular velocity. As input, we have the normalized steering input, which is the steering of the cars, and the throttle, which represents how much power we give to the wheels. Multiple experiments have been done in order to estimate the characteristic of the car. For example, we have estimated how much force the tire produced while the tire is slipping. For multiple slip angle, then based on these identifications, we simulate the cars in MATLAB and compare it to the data we collected on the physical system. The data looks promising. As you can see, we have very little gap between the physical system and the simulated one. Here is a video of the car in the simulators. At slow speed, it matches the reality, but at high speed, we are not sure if the behavior is correct or not. Then we formulate the MPC problem. Based on the state from the model, the car tries to follow a reference trajectory while maximizing the progressions along the track. It allows the cars to take a shortcut in order to maximize advancement. We use two types of MPC solver. The first solver is LAMI, which uses the interior port method, and the second solver is LAMP, which uses the SQP method. SQP is a faster solver because it uses the solutions of the previous iterations as the initial solutions for the current iteration. From the video, we can see that the LAMI controller solves about an iteration every second, and the LAMP controller can solve it 10 times faster at around 80 milliseconds. Multiple improvements are possible. So first, we could have a better identifications of the dynamics of the cars by conducting experiments at higher speed, and so having a better model. Secondly, we could also improve the SQP solver by tuning it more to our problems, which will lead to a higher stability in the systems and maybe a better solving time. In conclusions, MPC demonstrated effectiveness at low speeds, but faces computational challenges. Thank you for your attention.